Good morning. This is an audio recording for visually impaired student. Today I am going to read a chapter named Catalysis from Physical Chemistry written by Dr. H.C. Khetrapal. What is catalysis? A catalyst is a substance that change usually increase the rate of the reaction but is recovered chemically unchanged at the end of the reaction and the phenomena is called catalysis. Although a catalyst is not consumed, it does enter into a chemical reaction but is subsequently regenerated as will be discussed later in this chapter. Positive and negative catalysis. If a catalyst increases the rate of the reaction, it is called a positive catalyst and the phenomena is called positive catalysis. A few examples of positive catalysis are given below. First, decomposition of potassium chlorate in the presence of MnO2 as a catalyst. KClO3 solid in the presence of MnO2, it will give 2 KCl plus 3 O2. Oxidation of SO2 to SO3 using NO as catalyst. SO2 react with half O2 in the presence of NO, it will give SO3. Manufacturing of ammonia by Haber process using finely divided iron as catalyst. N2 plus 3H2 in the presence of iron, it will give 2 molecules of ammonia. Hydrolysis of ethyl acetate in presence of an acid or an alkali as catalyst. CH3COOC2H5 plus H2 in the presence of H positive or OH negative. It will give CH3COOH plus C2H5OH. If a catalyst decreases the rate of reaction, it is called a negative catalyst and the phenomena is called negative catalysis. A few examples of negative catalysis are given below. Decomposition of H2O2 is retarded in the presence of traces of acetanilidine 2H2O in the presence of acetanilidine give 2 molecules of H2 plus O2. Oxidation of chloroform is retarded in the presence of small quantity of ethyl alcohol. Chloroform react with O2 in the presence of C2H5OH give phosphosine COCl2 plus 2HCl. Third, tetraethyl lead anti-knock is added to petrol to stop chain reaction which cause knocking. The term catalysis used without any prefix always means positive catalysis. Autocatalysis. When in a reaction, one of the product act as a catalyst for the reaction, the phenomena is called autocatalyst. For example, in the titration of hot oxalic acid solution against acidified KMnO4 solution, the pink color is discharged first slowly and then rapidly as the reaction proceeds. This is because the Mn2 positive ion formed during the reaction act as autocatalyst for the reaction. 2 MnO4 negative plus 16H positive plus 2 C2O42 negative give 2 Mn2 positive plus 10 CO2 plus 8 H2O. 2 Mn2 positive act as an autocatalyst. The hydrolysis of ester by water is slow in the beginning, but the acid formed during the reaction act as an autocatalyst and subsequently the reaction is speed up. RCOOR dash plus H2O, it will give RCOOH plus R dash OH. Generally characteristics of a catalyst. First, a catalyst remain chemically unchanged at the end of the reaction. It may, however, undergo a change in physical state, color, etc. For example, MnO2 used as catalyst in the decomposition of KClO3 changes from coarse powder to fine powder at the end of the reaction. Second, a small amount of the catalyst is sufficient to bring about a large change in the speed of the reaction. Example, trace of platinum as catalyst are sufficient for large volume of H2 and O2 to combine to form water molecule. Third, a catalyst is specific in nature. A particular substance may act as a catalyst for one reaction, but the same substance may not act a catalyst even for similar reaction. Fourth, a catalyst does not initiate a reaction, it simply changes the speed of the reaction. Fifth, a catalyst does not disrupt the state of equilibrium of a chemical reaction. This is because it increases speed of forward and backward reaction to the same extent. Sixth, a catalyst shows maximum activity at a particular temperature called the optimum temperature. How does a catalyst work? A catalyst decrease the activation energy of the reaction. Example, lower the energy barrier and thus make the reaction fast and shown in figure 6.1. However, it may be noted in a reversible reaction. The catalyst decreases the activation energy of forward reaction as well as that of the backward reaction by the same amount. Thus, both the forward and the backward reaction are accelerated to the same extent. As a result, the equilibrium is attained quickly but is not disturbed. Promoter and inhibitor, catalytic poison. Sometimes the presence of some other substance which are not necessarily catalyst increases the efficiency of a catalyst. Such substance thus act as a catalyst for the catalyst and are called promoter or activator. Molybdenum act as a promoter for the iron catalyst in the manufacturing of ammonia by Haber process. Similarly, the synthesis of methyl alcohol from CO and H2 is catalyzed by zinc oxide mixed with chromium oxide and other oxide as promoter. In some cases, the presence of small quantity of impurities in the reacting substance make the catalyst inactive. Such substances are called catalytic poison or inhibitor. Catalytic poison are usually also poisonous to organism. Arsenic oxide and hydrogen cyanide are two of the most powerful catalytic poison. Arsenic oxide poison platinized as box used as catalyst in a manufacturing of H2SO4 by contact process. Homogeneous and heterogeneous catalysis. Homogeneous catalysis. When in a reaction the catalyst is present in a same phase as a reactant, it is called the homogeneous catalysis. Example of homogeneous catalysis take part in a gaseous phase. First, reaction between SO2 and O2 to form SO3 in the presence of nitric oxide. Decomposition of acetaldehyde in the presence of iodine vapor. Decomposition of gaseous of N2O at 1000 Kelvin in the presence of trace of chlorine gas. Decomposition of ozone in the presence of NO and N2O5. Gas phase dehydration of tert butyl alcohol in the presence of HBr gas. Example of homogeneous catalysis taking place in a liquid phase. A large number of examples of homogeneous catalysis has been studied in a liquid phase. This may be divided into two categories. First, acid-basis catalysis. Most of the examples of homogeneous catalysis in the solution are those catalyzed by an acid or a base. For example, first, hydrolysis of cane sugar sucrose in the presence of mineral acid called inversion of sugar cane. Sucrose plus H2O in the presence of H positive give glucose plus fructose. Hydrolysis of methyl acetate by an acid or a base. Hydrolysis of methyl acetate, it will give acetic acid plus methanol. Hydrolysis of starch to glucose in the presence of an acid. Hydrolysis of nitramide in the presence of a base. Nitramide in the presence of base give N2O plus water molecule. B. Homogeneous catalysis in solution other than acid-base catalysis. A very common example in a decomposition of water in the presence of I negative ion or Br2. H2O2 in aqueous state in the presence of I negative or Br2, it will give 2H2O plus O2 molecule. Mechanism of some homogeneous catalytic reaction. Intermediate compound formation theory. A homogeneous catalytic reaction usually takes place in a two-step as follows. First step, the catalyst react with the reactant to form an intermediate complex. A plus C give AC. Second step, the complex then either decomposes to form the product regenerating the catalyst or react with the second reactant to give the product and regenerating the catalyst. AC give product plus C, AC plus B give product plus C. This is illustrated with a few examples given below. Mechanism of the reaction, 2SO2 plus O2 in the presence of NO give 2SO3. First step, NO plus O2 give NO2. Second step, NO2 plus SO2 give NO plus SO3. Both the above steps are fast and hence the oral reaction is also fast, whereas in absence of catalyst the reaction is slow. Second, mechanism of the reaction. CH3CHO in the presence of iodine gives CH4 plus CO. First step, CH3CHO plus I2 gives CH3I plus HI plus Cu. Second step, CH3I plus HI gives CH4 plus I2. Mechanism of the reaction. 2N2O in the presence of chlorine give 2N2 plus O2. First step, chlorine give 2HCl, N2O plus Cl give N2 plus ClO, 2ClO give Cl2 plus O2. Mechanism of the reaction. 2O3 in the presence of N2O5 give 3O2. First step, 2N2O5 give 2N2O4 plus O2. O3 plus N2O4 give O2 plus N2O5. Mechanism of a reaction. 2H2O2 in the presence of iodine give 2 molecular water plus oxygen. First step, H2O2 plus I negative give H2O plus IO negative. Second step, H2O2 plus IO negative give H2O plus O2 plus I negative. Sixth step, mechanism of a reaction. 2H2O2 in the presence of Br2 give 2H2O plus O2. First step, H2O2 plus Br2 give 2Br negative plus 2H positive plus O2. Second step, 2Br negative plus H2O2 plus 2H positive give Br2 plus 2H2O. Kinetics of some homogeneous catalytic reaction. The mechanism of different reaction written above are obtained on the base of kinetic studies. The rate equation in the presence of catalyst is found out experimentally. This tells the type and a number of the different molecules taking part in the rate determining step, which then help to write the probability mechanism of the reaction. A few examples are explained below. First, kinetics of the decomposition of acetaldehyde in the presence of iodine vapor as a catalyst. The decomposition of acetaldehyde takes place. CH3CHO gives CH4 plus Cu. The observed rate reaction for this reaction is found to be rate is equal to minus D. CH3CHO by dt is equal to K1 CH3CHO की power 2. We suggest the mechanism as follow. CH3CHO plus CH3CHO give 2CH4 plus 2Cu. In the presence of iodine vapor as catalyst, the rate equation is observed to be rate is equal to minus D. CH3CHO by dt is equal to K2 CH3CHO into I2. This suggests the probable mechanism of the catalyst reaction as follows. CH3CHO plus I2 slow reaction K1 gives CH3I plus HI plus Cu called rate determining step. CH3I plus HI fast step K2 CH4 plus I2. Further at 600 Kelvin, the value of K2 is found to be about 10 to the power 7 times than the K1. The activation energy of catalyst reaction is found to be 138 kJ per mole as compared to 188 kJ per mole for the uncatalyzed reaction. Second, kinetics of the dehydration of third butyl alcohol in the presence of HBr. The dehydration of third butyl alcohol takes place as CH3 thrice CHO gives CH3 twice C double bond CHO plus water molecule. In the absence of catalyst, the alcohol does not decompose at any appreciable rate up to about 700 Kelvin. On additing a small amount of HBr, rapid decomposition occur at 500 Kelvin. The rate equation for the uncatalyzed reaction is rate is equal to minus D into third butyl alcohol plus dt is equal to K third butyl alcohol It is a first order reaction with very low value of K1. In the absence of HBr, the rate equation is observed to be rate is equal to minus T third butyl alcohol by dt is equal to K2 third butyl alcohol into HBr. It is a second order reaction with high value of K2. This suggests that a possible mechanism for the catalyzed reaction is CH3 thrice CeOH plus HBr slow reaction gives CH3 thrice CBr plus H2. This is a rate determining step. CH3 thrice CBr fast step. CH3 twice C double bond CHO plus HBr. This is supported by the fact that third butyl bromide is found to be intermediate. Third, kinetics of the journal acid-base catalytic reaction. A large number of reactions are catalyzed by acid-base, and hence acid and base can be taken as a substance on the basis of any of the acid-base concept. For example, substance that yield H positive and OH negative ion in aqueous solution, Arrhenius concept, proton donor and acceptor, Bronsted concept, or electron acceptor and donor called the Lewis concept. In an acid catalyst reaction, the first step is a transfer of proton H positive ion from an acid HA to the substrate S. For example, one of the reacting molecule S plus HA give SH positive plus A negative. Then this is then followed by one of the two possibility, either proton transfer to the solvent SH positive plus water molecule give P plus H3O positive. P is equal to product, or proton transfer to the base A negative uh, prototropic mechanism. SH positive plus A negative give P plus HA. Taking reaction first as a first step and reaction second as a second step, then taking the later as the rate determining step, the reaction rate is given by minus ds by dt is equal to K2 CH positive SH positive, but the rate of reaction of SH positive is given by dSH positive by dt is equal to rate of formation of SH positive from S and HA minus rate of formation of SH positive with water. K1 into S into HA minus K1 dash SH positive into A negative minus K2 SH positive. The steady state condition imply that the rate of the reaction of concentration of SH positive with time should be 0. For example, dSH positive by dt is equal to 0. Thus, K1 SHA minus K dash 1 SH positive A negative minus K2 SH positive is equal to 0. SH positive bracket open K negative K dash 1 A negative plus K2 bracket close is equal to K1 S into HA, or SH positive is equal to K1 into S into HA by K1 dash into A negative plus K2. Putting this value in equation 4th, we get minus ds by dt is equal to K1 into K2 multiply S into HA by K1 dash into A negative plus K2. Consider as equation 6th. If K2 is very less than as compared to K1 dash A negative, equation 6 become minus ds by dt is equal to K1 K2 S into HA by K1 dash A negative. That is considered as an equation 7. But for the weak acid HA plus water molecule give A negative plus H3O positive. So that the equilibrium constant for this acid base reaction is K is equal to A negative H3O positive by HA. HA by A negative give H3O positive by K. Substituted this value in equation 7, we get minus ds by dt is equal to K1 K2 by K1 dash K S into H3O positive, considered as equation 9. Thus, when an acid-base reaction is in equilibrium, the derived rate expression for the catalysis reaction becomes first order in H3O positive. Since the species H3O positive appear in a derivative derived rate expression, we say that catalysis is H3O positive specific. In the reverse condition, when K2 is greater than K1 dash A negative, the equation 6 reduced to minus ds by dt is equal to K1 S into HA, considered as equation 10. The catalysis is now brought about by the species HA and is first order in HA, and now as HA appear in the derived rate expression, the catalyst is said to be journal since it occurs for any acid HA. For the second possibility, taking reaction first as a first step and reaction third as a second step, then taking the reaction third as a rate determining step, the rate equation will be minus ds by dt is equal to K2 SH positive A negative. The rate equation for SH positive now will be dSH positive by dt is equal to K1 dSH positive by dt is equal to K1 SHA minus K1 dash SH positive A negative minus K2 SH positive A negative. And for the steady state condition, dSH positive by dt is equal to 0. For example, K1 SHA minus K1 dash SH positive A negative minus K2 SH positive A negative is equal to 0. SH positive A negative is equal to K1 SHA by K1 dash plus K2. Substituted in equation 11 we get minus ds by dt is equal to K1 K2 SHA by K1 dash plus K2. This is equation 12. As the concentration HA appears in the derived rate expression, and hence it is a case of journal acid catalysis. In a base catalysis reaction, the first step is a transfer of hydrogen atom from the substrate to the base. SH plus B, it will give S negative plus BH positive. As negative then further react, the expression for the rate can be obtained in a manner exactly similar to that of the acid catalyst reaction. It is also possible that a reaction may be both acid and base catalysis, and then overall reaction rate of reaction of the substrate is given by minus ds by dt is equal to K naught S plus Ka SH3O positive plus Kb SOH negative. Consider as equation 13, where K naught is the rate coefficient for the uncatalyzed reaction, K corresponding to the coefficient of the rate expression for an acid catalyzed reaction, and Kb is a similar coefficient for the rate expression for a base catalyzed reaction. At low pH, the second term dominate, whereas at high pH, the third term is most important. As an example, let us consider the bromination of acetone in aqueous solution. The reaction is thought to occur in the following two steps. First step, enolization of acetone. Second step is the bromination of enol. When the reaction is carried out in a neutral solution and a bromine is present in a larger excess, so that the first step is a rate determined step and the reaction is observed to be minus D CH3CO CH3 by dt is equal to K naught CH3CO CH3. Consider as equation 14. When an acid or a base is added, it accelerates the rate of enolysis and enhances the rate of overall reaction. In the enolization process, one proton must be removed from the methyl group and another added to the carbonyl oxygen. In neutral solution, this can be achieved with water alone. However, this process occurs more easily in the presence of acid and a base as shown below. In the presence of weak acid HA, say acetic acid, the two species HA and H3O positive both are present and each make its own contribution to the rate. And hence we have in the presence of an acid minus D CH3CO CH3 by dt acid give is equal to K1 CH3CO CH3 into H3O positive plus K2 CH3CO CH3 into HA. Consider as equation 15. Similarly, in basic solution, we will have the two species OH negative and B negative says acetate ion present, and hence the oral rate of reaction will be minus D CH3CO CH3 dt base is equal to K3 CH3CO CH3 OH negative plus K4 CH3CO CH3 Br negative. Consider as equation 16. When both acid and base are present, says in a buffer solution of acetic acid and sodium acetate, we must combine all these effects so that the complete rate expression is minus d CH3COCH3 by dt is equal to K naught CH3COCH3 plus K1 CH3COCH3 into H3 positive plus K2 CH3COCH3 into HA plus K3 CH3COCH3 into OH negative plus K4 CH3COCH3B negative plus K5 CH3COCH3 into HA into B negative. Consider as equation 17. The last term K5 account for the simultaneously attack of an acid on an oxygen and base on a methyl group. Another well-known example of an acid-base catalyzed reaction is mutation of glucose. Example, change of alpha glucose represented as GH to beta glucose represented as Hg. The change is believed to take place through the following step. CH plus H3O positive give HgH positive. Intermediate complex plus water give Hg beta glucose plus H3O positive. Proton removed by the base catalysis. In the first step, proton given by H3O positive is taken up by the glucose, whereas in a second step, proton is taken up from the intermediate complex by H2O complex to form H3O positive. Thus, both acid and a base are needed for catalysis. This is further confirmed by the fact that mutation of glucose is very low if only an acid aerosol is added as catalysis or only a base. Pyridine is added as catalysis as the reaction is quite fast if both are added. Heterogeneous catalysis or surface catalysis. When in a reaction, the catalyst is present in a different phase than that of the reactant, it is called heterogeneous catalysis. The catalysts are usually solid, whereas the reactant are gaseous or liquid. The reaction occurs at the surface of catalyst. This is why this type of catalyst is also called the surface catalyst or contact catalysis. Evidently, greater is the surface area of the catalyst, greater is the efficiency of the catalyst. For this reason, finely divided solid are usually used as a catalyst. As heterogeneous catalysts stay in position and can be readily recovered, they are much more widely used in industries than the homogeneous catalyst. Example of heterogeneous catalytic reaction. First, manufacturing of ammonia from nitrogen and hydrogen using finely divided iron as a catalyst. N2 plus 3H2 in the presence of finely divided iron give 2 molecules of NH3. Formation of SO3 from SO2 and O2 in the contact process for manufacturing of H2SO4 using finely divided platinum or vanadium pentoxide as catalyst. Manufacturing of methyl alcohol from CO and H2 using ZNO and Cr2O3 as catalyst. Hydrogenation of oil using finely divided nickel as catalyst. Fifth, decomposition of N2O in presence of gold. N2O it will give to N2 plus O2. Demonstration that heterogeneous catalysis is surface catalysis. Consider the bromination of ethylene. Bromination of ethylene it will give BrCH2 single bond CH2Br. This reaction takes place readily in a glass vessel at 470 Kelvin and was thought to be an ordinary homogeneous catalytic reaction. However, it is found that the rate is higher in a smaller reaction vessel or in a vessel packed with glass beads, but the rate is reduced when the vessel is coated on the inside with the paraffin wax. This shows that the reaction is not occurring in a gaseous phase, but it occurring on a glass surface of the vessel and the glass is acting as a catalyst, demonstrating the specificity of a heterogeneous catalyst. Consider the decomposition of formic acid. If the acid vapor is passed through a heated glass tube, the reaction is about 50% dehydration and 15% dehydrogenation. First, HCOOH give H2O plus CO. Second, HCOOH give H2 plus CO2. If the tube is packed with Al2O3, only reaction first occur. If it is packed with ZnO, only reaction second occur. Mechanism of heterogeneous catalytic reaction. Adsorption theory. It is believed that a heterogeneous catalytic reaction takes place through the following sequence of steps. Diffusion of the first diffusion of the reactant molecule toward the surface of catalyst. Second, adsorption of the reactant molecule on a surface of the solid. The site at which the reacting molecule are adsorbed are called the active site. Third, chemical reaction of the adsorbed molecule with the surface of the catalyst resulting into stretching and wicking of bond forming an activated complex with the catalyst which then decompose or even breaking of bond of reacting molecule. Step second and third are jointly called chemosorption. Fourth, desorption of product from the surface. Fifth, diffusion of the product away from the surface. The various steps are illustrated with example. First, hydrogenation of ethylene in the presence of finely divided nickel platinum palladium. Ethylene in the presence of nickel platinum, it will give ethane. Second is a decomposition of HI in the presence of platinum. 2 HI in the presence of platinum give H2 plus I2. The mechanism for this reaction may be represented as follows. HI plus platinum give HI platinum attached to the hydrogen. After that a transition state form, and after that transition state decomposed to product platinum plus half H2 plus half I2. Kinetics of the heterogeneous catalytic reaction, surface reaction. It has already been explained above that a heterogeneous catalytic reaction take place in fine consecutive steps, although any of these steps may be slowest and hence rate determining. Yet from the point of view of study of kinetics of this reaction, step third, the reaction of adsorbed molecule is considered to be the rate determining. Further, the rate of reaction is supposed to be proportional to the fraction theta of the surface covered by the reactant molecule. Thus, two assumptions in a study of kinetics of the surface reaction are: first, the rate determining step of surface reaction is the reaction of the adsorbed molecule with the surface of the catalyst. Second, the rate of reaction is proportional to the fraction theta of the surface covered by the reacting molecule. The detailed study of kinesis of this reaction has already been discussed in chapter 5. Action of catalytic promoter and inhibitors. Promoter are the substance that enhance the activity of the catalyst. They are in fact catalyst for the catalyst. They may not act alone as a catalyst for the same reaction or may act only a Fable catalyst. A well-known example in a manufacturing of ammonia from N2 and H2 by Haber process in which iron is used as catalyst and molybdenum used as a promoter. N2 plus 3H2O in the presence of iron catalyst, MO promoter give 2 ammonia molecule. The action of promoter is explained on the base that the lattice defect or the irregularity on the surface of catalyst are the active site for catalysis. The addition of the promoter encourages the formation of lattice defect and enhances the active sites. Consequently, the activity of catalyst is enhanced. Inhibitors or catalytic poison are the substances that inhibit, diminish the activity of the catalysis. A few examples are given below. First, oxidation of SO2 to SO3 by oxygen in the presence of platinum as catalyst, it's slowed down if arsenic is present. Second, hydrogenation of ethylene in the presence of copper is slowed down if CO is present. Oxidation of sodium sulfide by oxygen in the presence of minute concentration of cupric ion is greatly retarded if cyanide ion are present. The action of inhibitors is explained in different way as follows. First, the catalytic poison may have a strong preferential adsorption on the surface of catalyst. Thus, the entire surface of the catalyst may be covered with the catalytic poison and no adsorption. of the reactant may take place on a catalytic surface. Example second above in a case of this type. Second, the catalytic poison may react chemically with the catalytic surface and form a new surface which may be catalytic inert. For example, the catalytic poison arsenic react with platinum to form platinum arsenide at the surface. The fact that a very small amount of poison is sufficient to stop the activity of the catalyst completely in certain cases has led to the suggestion that the surface of catalyst is irregular with the high catalytic activity only at certain spots on the catalytic surface. As soon as these spots are covered with the poison, the activity of the surface reduced to almost zero. Enzyme catalysis. Enzymes are protein molecules present in the living system. Their molecular mass range from 10 k power 4 to 10 k power 6 gram per mole and their diameter lie in range 10 to 100 nanometer. They are highly efficient biological catalysts which catalyze the reaction taking place in a living cell and also help in controlling their reaction rate. The number of enzymes present in a living cell is very large. For example, it is estimated that a typical mammalian cell contains 10 k power 4 different enzymes. The reaction that the enzyme catalyst occur at a specific site on the proton molecule, this is called the active site, and the reactant in an enzyme reaction are generally referred to as substrate. Since enzymes are very effective catalysts, they are usually used in laboratory experiment at the concentration much lower than the concentration of the substrate. A few examples of enzyme catalyst laboratory reaction are given below. First, starch in the presence of diesterase give maltose. In the presence of maltose give glucose. In the presence of jamase it will give alcohol plus CO2. Second, cane sugar. In the presence of invertase it will give invert sugar, glucose plus fructose. In the presence of jamase it will give alcohol plus CO2. Name of enzymes are written on the arrow. Enzyme possesses certain characteristics which are different from other type of catalyst. A few of these are brief discussed below. Their efficiency is very low. Many of them are so powerful catalysts that they increases the rate of reaction by many order of magnitude even at quite low concentration. They are highly specific in their catalytic action. For example, urease, even in very low concentration, catalyzed the hydrolysis of urea, but it has no detectable effect on the hydrolysis rate of subsequent urea such as methyl urea. There are many such examples to quote. However, there are some exceptions to this generalize as many enzymes are efficient to some extent with a variety of substrate having similar property. Third, they are highly sensitive to temperature. The activity of the enzyme is usually found to maximum at the normal temperature of the organism in which the organism is found. Above this temperature, usually the activity is first found to increase temporarily and then drop to zero when the protein is denaturated. A typical curve of activity versus temperature is shown in figure 6.3. Fourth, they are highly sensitive to acidity or basicity of the solution. It is found that the enzymes show a sharp change in the activity if the pH of the solution is changed. The activity is found to be maximum in aqueous solution at pH of about 6.4. The plot pH versus activity is similar to that of the shown. Mechanism or kinetics of the enzyme catalyzed reaction, Michael-Menten equation. The mechanism of an enzyme reaction as proposed by Michael and Menten in 1913 is as follows. The first step is in the enzyme reaction is the reaction between the enzyme E at the active site and the substrate S. For example, the reactant of the enzyme reaction to form the complex ES. E plus S give ES. The reaction is very fast and the equilibrium is rapidly established. The complex then dissociated forming one or more product P and regenerating the system. Enzymes ES give EP plus 2 consider as equation second. This reaction usually goes to completion so that the rate coefficient K2 dash is efficiently 0. The step first and second can be written together as E plus S give ES give E plus P. Consider as equation third. Thus, the enzyme substrate complex ES is an intermediate and the net reaction is S converted into P. As a result, the rate of appearance of the product must be equal to the rate of disappearance of the substrate S. dP by dt is equal to minus ds by dt. Consider as equation fourth. The condition implies that the concentration of the complex ES represented by ES must be in steady state. In other words, the rate of change of concentration of ES with time must be equal to 0. But the rate of change of concentration of ES with time will be given by uh, dES by dt is equal to rate of formation of ES from E and S and minus rate of decomposition of ES into E and P is equal to bracket open K1 E into S minus K1 dash ES bracket close minus K2 ES treating equation fifth. For steady state condition d ES by dt is equal to 0 and hence K1 E into S minus K1 dash ES minus K2 ES is equal to 0. ES bracket close K1 2 plus K1 dash is equal to K1 E into S. ES is equal to K1 E into S by K1 dash plus K2. This expression gives the steady state concentration ES. Consider this equation sixth. Putting K1 dash plus K2 by K1 is equal to Km called Michael constant expression 6 can be written as ES is equal to E into S by Km. Consider equation 7. Since ES is a steady state, we must have rate of disappearance of S is equal to rate of disappearance of ES. Minus ds by dt is equal to K2 ES. Consider as equation 8. But the rate of disappearance of S means the rate of enzyme catalyst reaction, usually represented by V, called steady state velocity, and hence V is equal to minus ds by dt is equal to K2 ES. Substituting the value ES from equation 7 in equation 9, we get V is equal to minus ds by dt is equal to K2 ES is equal to K2 ES by Km. Consider as equation 10. The equation is, however, not usually in this form since it concludes the concentration of free enzyme E where the experimentally measurable quantity is E naught. The total concentration of enzyme, for example, free as well as combined in a complex is, but we have E naught is equal to E plus ES so that E is equal to E naught minus ES. Substituting this value in equation 7 as we get ES is equal to E naught minus ES bracket close into S by Km, or Km into ES is equal to E naught into S minus ES into S, or Km ES plus ES into S is equal to K naught into S, or ES bracket start Km plus S bracket close is equal to E naught into S, or ES is equal to E naught into S by Km plus S regarding equation 11. Substituting this value in equation 9 as we get V is equal to minus ds by dt is equal to K2 ES is equal to K2 E naught by S by Km plus S regarding equation 12. This equation is known to be the Michael-Menti equation, which contain the measurable quantity E naught and S. The equation 12 is usually written in the term of maximum velocity Vm of the enzyme catalyst reaction, which is reached when S becomes so large so that S is greater than Km, so that Km can be neglected in comparison to S. The equation 12 take the form Vm is equal to K2 E naught. Regarding equation 13, V by Vm is equal to S by Km plus S regarding equation 14. From this equation, we find that when S is equal to K, V by Vm is equal to half, V is equal to half Vm. Thus, Michael constant is equal to that concentration of the substrate at which the rate of enzyme catalyst fall to one half of its maximum value. Thus, the value of Vm and Km can be obtained by plotting the rate of equation versus the concentration of the substrate. The graph of this type is shown in figure 6.4. The value of Vm and Km can be obtained as regarding. Alternatively, to convert equation 14 into a linear form, it may be obtained in form Vm by V is equal to Km plus S by S. Vm by V is equal to Km by S plus 1. 1 by V is equal to Km by V1 into 1 by S plus 1 by M regarding equation 15. Thus, a plot of 1 by V versus 1 by S will be a straight line, will intercept 1 by Vm and slope Km by Vm. The value of Vm and Km can be neglected. Further, since A naught is known using equation 13, K2 can be calculated as Vm has already been obtained. However, K1 and K1 dash cannot be determined. Order of enzyme catalyst reaction. Some interesting result about the order of enzyme catalyst reaction follow the Michael-Menti equation 12 as explained below. First, at low concentration of the substrate S can be neglected is comparison to Km in equation 12. As we have V is equal to minus ds by dt is equal to K2 by Km into E naught into S, or Vs is equal to minus ds by dt directly proportional to E naught into S, and hence the reaction is of second order. Second, if the enzyme concentration is kept constant and the concentration of substrate is varied, the reaction become of first order. If the substrate concentration is so high that Km is less than S, equation 12 reduced to V is equal to minus ds by dt is equal to K naught E naught. Thus, the rate of equation become independent of the concentration of the substrate. For example, it becomes zero order with respect to substrate. Thank you.